Once more, welcome, my dear students. I can see Floria is here. That's Floria, right? And Ruby. I hope the rest of the students join us very soon. So without much ado, I'm going to go straight to the topic of today. We are talking about direction of friction. Which should be a very easy topic to comprehend. So we will just go through a few readings. I will first summarize something, summarize about direction, and then we will go through some reading from your book and solve some problems. Okay? So far, we know that until now, we know that friction can be divided into static friction, and static friction is the value is less than or equal to mu r. If object is at rest and no force is trying to pull the object to slide against another object, then friction will be 0. But if the force starts to increase, the static friction will increase until it will reach a value of mu r. When it reaches a value of mu r, if the force increases beyond the static friction, then the object will start to slide. When the object is sliding, then we will have kinetic friction on the object. And in this course, we assume that kinetic friction is the value of mu r. Always, that's what we know so far. Now, you will encounter problems like this. For instance, you have a box here, and you don't continuously push it, you just give it some sort of an impulse. You push it very quickly and you take away this force. After you push it, it starts to move, you take away this force. And then you'll be asked questions like, how far does it travel here? So during this time that it is traveling, the only force that is acting is friction. And that is kinetic friction, Fk, which is mu r. And the object is then accelerating, you find the acceleration. So in this case, if there is no other force acting, then your frictional force, Fk, should be equal to ma. And you'll see that, remember that my direction of A and my direction of friction is opposite. So I'll use negative sign here. So minus Fk equal ma. So your A will be negative Fk over m. So after you then find the acceleration, you will use the value of this acceleration and your Suvat equations to find like how far the object will travel, s. You'll find s, right? Using your acceleration that you have found here. In some cases, you may have a problem like on an inclined plane. they will tell you that an object is on an inclined plane and it is pushed up the inclined plane given an impulse. You just give it an impulse and then you take away the force. Let me give a practical example. You may be told that somebody was on a hill, on a mountain. The person slides down. You'll be told how high this mountain is. And then the person slides down. As he reaches the bottom, he slides up a rough inclined plane. This plane is inclined at some angle, theta. This person slides freely down. So you should know the person's velocity at this point, right? And then they will ask you, at what point will the person stop on this hill? You analyze the problem the same as we have analyzed the other one. At any point on this hill, what will happen is you have the weight mg, you have the normal contact force R, and if no other force is acting here, then R is equal to mg cos theta, right? And then you have mg sine theta here, and this object is moving up, so you assume the acceleration to be parallel to the slope and upwards, A. And now you know that when you resolve perpendicular, you get R equal mg cos theta. I did not include the frictional force. The frictional force here, F, or Fk if you wish, you know that F is equal to mu R. So that's mu mg cos theta. And now, as this object is sliding up, you need to look for the acceleration and then use the acceleration to find the velocity at which, how far it moves up this slope. That's to find S, because your U would be something you know here. Your V would be 0. It will have to stop there before it slides back down. So you need to find your acceleration in this case. So from here, since F and mg sine theta are in the opposite directions of acceleration, so we resolve parallel to the slope. And since these two directions are opposite, we will have minus F minus mg sine theta should be equal to ma. And so you can find your acceleration. A should be minus mu mg cos theta, because your F is mg cos theta, minus mg sine theta divided by m. What does this give us? A should be negative mu g cos theta minus mu g minus g sine theta, no mu there, minus g sine theta. So it's g times negative mu cos theta. Maybe we put the negative sign outside. So that gives us negative g times mu cos theta plus sine theta. This is not a formula for you. I'm just showing you how you can find the acceleration for such a problem. And then after you know the acceleration now, you should be able to find, if you know your initial velocity u, some value, now you know that when it gets to its maximum point, it will come to rest. So v should be 0. Acceleration should be negative g, whatever you have here. It will give you that value. Call it negative a. Just call it negative 4. Let's say it's negative 4, for example. So acceleration is negative 4. And then you need to look for your s. For instance, you just substitute this in the equation v squared equal u squared plus 2as to look for your s, or any other equation and whatever you are looking for. Now, in some cases, you will be asked the question, when this object, when it arrives the maximum point, you'll be asked to determine whether it stays here or it slides back down. Does it slide back down or it stays there? How do you analyze such a case? You have to know that once the object reaches this point, this frictional force will automatically change direction. Friction will be facing that way, and the value is not the same as this value here. This value was mu r, this was mu r. When it changes direction, and if it stays here, then this friction here will be less than mu r. Okay? And if it has to slide down, what did I say? If this object should stay here, if it has to stay here, it means that this force, mg, because you only have mg sine theta now acting parallel to the slope downwards. If it has to stay here, then mg sine theta must be less than, it must be less than mu r. Okay? If this force is smaller than mu r, then the frictional force that has changed direction, then the friction that will be acting here now will just be enough to keep this object at rest. Right? So this friction will also be less than mu r. So I was right. This friction will be less than mu r. And its value will be mg sine theta. So actually, to determine whether the object stays at rest here or it slides back down, you have to just determine whether mg sine theta is bigger than mu r or is smaller or equal to mu r. It should be smaller than or equal to. If mg sine theta is equal to mu r, then the object will stay here. It will not slide down. But if mg sine theta is bigger than mu r, then the object will accelerate back downwards, right? And in some other cases, you will also be asked to find the speed with which the object reaches the bottom. For instance, you'll be asked to find the speed with which the object arrives here if it slides down. So in that case, you have to find the acceleration downwards, right? So it is a two-stage problem: the acceleration upwards and the acceleration downwards. The acceleration upwards and downwards will not be the same. So you have to solve two problems. In this case, you solve this first one, and then for the second one, you will have mg sine theta. You resolve parallel to the slope. So you have mg sine theta minus F minus the frictional force minus F, which in this case, if the object is sliding down, then F will be equal to mu r, right? This will be mu r. So this will be equal to ma. And so you can find the acceleration downwards, which is mg sine theta minus mu r is mu mg cos theta over m. So your acceleration will be g into sine theta minus mu cos theta. You can see here that your acceleration downwards is very different from your acceleration upwards. Not only in this negative sign, but the magnitude also is different. The magnitude of the acceleration downwards is different from the magnitude of the acceleration upwards. So what does this negative sign here for acceleration tell us? The negative sign is telling us that as the object is moving up, it is slowing down. And this one remains positive to tell us that when the object now reaches here, and if it has to slide down, then it will be accelerating, it will be increasing speed downwards. Okay? So this simple fictitious problem explains how you analyze problems in which friction has to change direction. Okay, let us look at some problems, some questions. Sorry about the noise, guys. Let us look at these questions. Exercise 4C, I'll solve these ones. I'll solve the odd numbered ones. And then you will solve the even numbered questions at home. Question 5. Hope that we are able to solve those three. I didn't find out who is not here and who is here. And I just okay. Let us look at question 1. It says, at the end of a downhill run, this seems like the problem I just solved. A skier of mass 80 kilograms slides up a rough slope at an angle of 10 degrees. So he goes downhill run, and then slides up. It seems like what I just illustrated. And this angle is 10 degrees. Slow down. He arrives at the upward slope with an initial speed. He arrives here with an initial speed u of 12 meters per second. The coefficient of friction, mu is 0.4. Find how far up the slope he comes to rest and show that he remains at rest there without falling back down the slope. I think this problem is exactly what I illustrated. So as he is moving up, we have his weight here is 800 newtons. So you have 800 gosh, 800 cos 10 here. And there's the normal reaction there. And there's 800 sine 10 here. (800 sine 10). And the acceleration is up the hill, A. And there is friction. I almost always forget this friction, you know. Let's call the friction F. So resolve perpendicular, we have R is equal to 800 cos 10. You may want to calculate that value, 800 cos 10. Let me quickly calculate it. (800 cos 10). What is that? My calculator is in radians, so always remember to put it in degrees if you have to make a calculation. 800 cos 10. I have 787.85. So R is 787.85. newtons. So your frictional force now will be mu r. That should give us times mu times 0.4. Just use the result in the calculator times 0.4. We get 315.14. 315.14. That is the frictional force. So now we resolve parallel to the plane. We get minus 315.14 minus 800 sine 10 should be equal to the mass of the person is 80 A. So we get A to be equal to negative 315.14 minus 800 sine 10 divided by 80. Okay, I'll go back to my calculator. I'll put negative answer minus 800 sine 10 equal. I get that, I divide it by 80. I get negative 5.68. So acceleration is negative 5.68. Is that all we are asked to look for? How far he moves up the slope before coming to rest. So U is 12. V is 0. A is negative 5.68. And S, we don't know. V squared equal U squared plus 2AS. That gives us S to be V squared minus U squared over 2A. That is equal to 0 minus 12 squared divided by 2 times negative 5.68. So it's 144 over 2 times 5.68. 2 times 5.68. I do the calculation. 144 divided by 2 times 5.68. 12.68. So 12.68 meters. So what it is saying here is that he will move 12.68 meters along this line, okay? It is not height. In the future, when you will have problems in the future, you may be asked to find how high he goes up. That will be different from this distance, it is 12.68 along the slope. And now you are asked to show that he remains at rest there without falling back down the slope. So you have to give a little bit of an explanation here. You know that your mu r is 315.14. 315.14. And then now, you have to explain that when he arrives up the slope, the frictional force will change direction and look upwards. And 800 sine 10. 800 sine 10. You have to show that this 800 sine 10 is less than 315.14. Therefore, the frictional force when he arrives up the slope will be exactly this value, and so he cannot accelerate back down. Okay? Just that. We have 8 minutes left. I think we can only solve one problem. It says a bulk of mass 3 kilograms is at rest on a rough slope at an angle of 15 degrees to the horizontal. It takes a force of 20 newtons parallel to the slope to break equilibrium and jack it up the slope. Find the coefficient of friction. So you have 15 degrees here. A bulk is lying at rest here. When the bulk is at rest, the frictional force is exactly equal to mg sine theta. But now it takes a force of 20 newtons to break the equilibrium prior to the slope, to break the equilibrium and jack it up. So you have 20 newtons here. You have R there. And then you have mg sine theta here. And you also have mu r here. So we are saying that this force just breaks the equilibrium. So when you just apply this force, the object will be in a static, will be in a limiting friction. The friction here will be limiting, and but still the object will be in equilibrium. And when it is just a little bigger than this, it will start to accelerate upwards. In this case, it's not accelerating yet. So your 20 newtons should be equal to mg sine theta plus mu r. And then you can find mu from that. Find the acceleration of the bulk down the slope if the 20 Newton force is applied downward instead. Now, when the 20 Newton force is applied downwards instead, this force remains. Mg sine theta stays downwards, but now the frictional force is upwards, and that friction is still mu r. And then the object accelerates down. So now again, you resolve parallel to the slope. You will get This is your 20 newtons. So you'll get 20 plus mg sine 15 should be minus mu r. Minus mu r. This should be equal to ma. Okay, and then you can find the acceleration. I think we don't have much time left. I don't know if I can do question 5, but maybe it should be the same kind of problems. A car of mass, this, is at rest on a rough slope at an angle of 35 degrees to the horizontal. It takes a force of 13,000 newtons to move it up the slope. Show that without any force, the car would slide down the slope, and find the minimum force to prevent it moving down. Okay. So this here, this is the same as question 3. So it takes a force of 13 newtons to move it up the slope. So it means that when it is in limiting equilibrium, you have this force 13,000 newtons, and you have the frictional force here, which is mu r. And you also have mg sine theta there. And this is in limiting equilibrium. So you resolve parallel, you should have mu r plus mg sine theta should be equal to 13,000. You can use this to find mu, or mu r. You already know r, so you should use it to find mu. And then the question says, you should show that without any force, the car will slide down the slope. So now you should show that in this case, you should show that mg sine theta without any force, mg sine theta is bigger than mu r. You should show this. Okay? If mg sine theta is bigger than mu r, then when you just place the object here, it will slide down because the frictional force will be acting upwards now. And it says you should find the minimum force to prevent it moving down. In this case now, you have, let me draw a different diagram now. In this case now, you should have an additional force here, F, which you should find, and you still have your frictional force here, which is mu r, and then you have your mg sine theta here. So now mg sine theta should be equal to mu r plus F, and so you can find F from there. That would be the minimum force to keep it from sliding down. Okay, that is it. We don't have much time left. So I have to say bye-bye. I'll see you guys on Monday, okay? Tomorrow you'll have some work to do. For today,